Okay, thank you. So let's start, and thank you for inviting me. And let's start the lecture number 7 of the DeCifrisTrends. I will talk about private set intersection, and my name is Carlo Blundo, and I'm from the University of Salerno. Let's define the problem. It's a very simple problem. We have, as usual, two participants, Alice and Bob. And Alice and Bob have a set of values. Let's say Alice has a set SA and B, and Bob has a set SB, and both are taken from a universe U. Alice and Bob want to compute the value in the intersection, the common value. So it's a very simple problem, and we know how to compute it. But the problem is that we want to preserve the privacy of the values in their set. So Alice and Bob want to compute a function of their input while preserving privacy. So, but do we really need to compute set intersection in a privacy preserving way? Let me give you a couple of examples. Assume that we have the IRS, the International Revenue Service. In Italy, we have the Agenzia delle Entrate, and we have a foreign bank, and the Agenzia delle Entrate wants to learn if suspect tax evader have a bank account. So the IRS has a list of possible tax evader. The foreign bank has a list of their customer, and they want to jointly compute the intersection of the entry they have. Or another example, we have the Central Intelligence Agency, and we have the Italian Secret Service. They want to collaborate. They both have a database of possible terrorists, and they want to learn whether there is some terrorist in both sets. Obviously, they don't want to share the whole database, so they want to compute a function of their database showing the elements in both datasets. We can model this functionality Alice and Bob want to compute by means of a secure two-party computational model. So in the real world, we have Alice and Bob. Alice has a set SA and Bob has a set SB. There is a trusted third party, and Alice and Bob sends their sets to the TTP. So it's simple for the TTP to compute any function of the sets SA and SB. In particular, they can compute the intersection of both sets. Once the intersection is computed, the results can be sent to Alice and Bob. In a more general scenario, Alice and Bob could receive different outputs. So we have two functions, FA and FB, that can compute on the inputs and SA and SB, and the value of FA is sent to Alice, and the value of FB is sent to Bob. So in particular, we can model the function FA and FB as in this slide. So Alice will get the intersection, the elements in common between SA and SB, while Bob will get the output of this function that is none. So Bob will not get any information about the intersection. This is the ideal world. But in reality, you have to run some computation between Alice and Bob. So there is a protocol. So they exchange some messages following some predefined rule, and at the end of the protocol, Alice will get FA and Bob will get FB. Obviously, there should be some relation between real world and ideal world, so that the two worlds should correspond in some way. The property that have to be satisfied are two. Correctness means that the protocol outputs in the two worlds are identical. So in the real world, we can compute the same information computed in the ideal world. And then there is the privacy. The privacy problem is can be modeled in considering two sides. The Alice privacy, from the Alice point of view, Bob should learn nothing about the input held by Alice. Maybe he can compute the size of the input, so he can know how many elements are in the set held by Alice. On the other hand, the Bob privacy point of view, Alice should not learn nothing about Bob inputs. Obviously, Alice can learn the elements in the intersection. And on top of that, she can compute also the number of the elements in ANSB, but that's it. So in private intersect intersection problem, we have the two participants as Alice and Bob. There is a PSI protocol, so some messages are exchanged between Alice and Bob. I'll show you a couple of simple example of PSI protocol. And at the end of the protocol, Alice will compute the intersection of the two sets, and Bob will compute nothing. In the protocol, I'll show you there is some leaking in some sense. Alice will learn the number of elements in Bob sets, and as well Bob will learn something more than none. He will learn the number of elements in the Alice set. So we can modify the output. We can say that the function learned by Alice is the intersection plus the sites of Bob sets, and what is learned by Bob is just the sites of the Alice sets. Once we have seen that is the general model for the protocol, we can model so any protocol by considering the ideal model and the real world. We have to model all the adversaries as well. We can have very simple adversaries, which is called honest but curious. It's also called semi-honest. This kind of adversaries follows the protocol specification, so it follows the rule outlined in the protocol, does not modify the message sends and does not modify the inputs, but is curious. So during the protocol execution or at the end of the protocol, these adversaries will try to infer some additional information about other players' input. The malicious is a stronger type of adversaries. It can behave like an honest but curious adversaries, but it can deviate from the protocol specification, so you can refuse from sending messages or can alter message and input. This is the protocol within this model are more difficult to build and to so in this lecture I will concentrate on simple protocol in the honest but curious scenario. Let me start with a very simple protocol, which is an unsecure protocol. First of all, Alice and Bob must encode their inputs. So they can have strings, they can have integer, they can have float, image. They have to agree on a common encoding. The first things we can think of is that Alice and Bob can encode their inputs by using the hash function h. So it's Bob. The protocol from the Bob point of view is quite simple. Bob computes the set xb, which is just the encoding of all the items in his set. So he computes the h of y for hy in he possesses, and send this set to Alice. At this point, Alice can compute the intersection simply by checking for each x in the set as a, whether the hash function computed on x belong to the sets received by Bob. This is obviously the sets computed is equal to the intersection. The protocol is very simple, but it's insecure. It's completely insecure. Well, actually, Alice's privacy is preserved since Bob does not learn anything. Bob is sending some information to Alice, not vice versa. But Alice can easily verify whether a value z belongs to Bob's value. She simply compute the hash function on z and check whether the computed value, the hashed value, belongs to the set received by Bob. If so, then with that probability, there is another set that will belong to the set SB. So the protocol is unsecure. We cannot use it, but we can borrow some idea from this protocol. So let's switch to a simple secure protocol. The basic idea is that still Alice and Bob have to encode their inputs, but the encoding must be done jointly. So Alice and Bob have to compute in a joint way, I'll show you in a moment, the encoding of the input. And the hash function is used to change the format in some sense of their input. They will use this hash function to map their values to a set. In general, it will be a multiplicative group where some operations in these particular sets are possible, are easy to compute. For instance, in a multiplicative group, we can easily compute an exponentiation, while other operations are difficult to compute. For instance, in a multiplicative group, if we choose the multiplicative group in a suitable way to compute the discrete log of an element, it's an hard problem. So we use this due property. And the protocol, the secure protocol goes as I'll show you in a moment. We still have Alice and Bob. Alice choose a value alpha and Bob a value beta. We can consider alpha and beta as kind of private key for Alice and Bob. And notice what is written in the green box. If we have two values, V belonging to Alice and W belonging to Bob, if the two values are the same, then if you compute the hash values of V and raise it first to alpha and then to beta, we get the same value computing the hash value of W, raising to beta and then to alpha. This is why we choose H, the hash function H, mapping values in a multiplicative group where exponentiation can be done. So Alice encode the values, takes each values in the set, computes the hash function, and raise the computed value to the alpha, strip off the value V from this encoding, and send this set to Bob. So in some sense, it takes the set, apply the hash function, and raise the hashed value to the alpha. Bob behave in a similar way. So he does the similar operation on his set. It takes all the value is in his set, computes the hash function, and then raise to beta, and then operate on the set received by Alice, raising the value received by Alice to beta. So there is a double encoding. Each value held by Alice is encoded first by alpha and then by beta, and send both sets to Alice. At this point, Alice can compute the intersection. He has to do some computation. He can compute the sets where to each item in her sets is associated an encoding of the item raised to alpha to the beta. He can extract apart from this information another part from this information, so you can link V to this encoding, and then takes the set SB raised to beta and raise all the elements in the set to the alpha. So it's a very simple operation. It does the same operation done on her values on the values held by Bob. At this point, you can see there are two sets where the hashed value are encoded by alpha and then by beta. And if we recall this property, then Alice can easily compute the intersection between SA and SB. So the protocol follows the line of the simple protocol, which is unsecure. We just add a security layer to the idea I just showed a few slides ago. Just for privacy reason, I want to go into the detail of the proof that the protocol is private, but instead of sending the sets in plane, as we showed in the slide, we have to shuffle the order of the elements in these sets. Just a short note on the implementation. So if you want to implement the protocol, we have to consider an hash function with the property I showed you before. So from universe U, which can be all the strings of length 1,000, to a group G. And in general, the group G could be a standard group. Is called the prime 256 version 1, which is based on elliptic curve group from NIST, so it's standard. And we choose this group because we can choose this group because the elements in the group are quite short. They are very, very short. They take just 256 bit. And then we can use a standard technique to map any value to points in the curve. So there are algorithms to do this, described in the document you can see in the bottom corner of the slides. This is just if we want to implement the protocol. And now I switch to another protocol, which is based on polynomial and to partial homomorphic encryption. So we use different with different tools. We have to use a partial homomorphic encryption schemes, which is an encryption schemes, so we can encode values, but we can do some operation on the ciphertext. So let me show what we can do. Suppose that we have two encryption of X and Y. So PK is the public key, and we have a constant C. We can compute some function of X and Y without knowing the secret key. For instance, we could compute the encryption of the sum of XY, depending on the protocol we use. This could be computed by multiplying the excuse me, the ciphertext corresponding to X and to Y, or we can, using the encryption of X and the constant C, we could compute the encryption of C time X. For instance, in some encryption scheme, we can compute this value, the encryption of C time X, just raising the encryption of X to the C. So we need a particular encryption scheme with some specific property, and there are plenty of homomorphic encryption scheme, for instance, Perrier, Galmal, Dagmar, Jewett. Now, we have to represent the set of Alice and Bob. Instead of hashing the values to a multiplicative group as seen in the previous protocol, we represent the set as using a polynomial P of degree K, assuming this in the set S there are K value, S1, S2, and Sk. And the polynomial is particular. In the sense that the values S1, S2, Sk are the roots of the polynomial. This is quite simple to compute. As you can see from the slide, we just compute the polynomial, the product of this monomial X minus Si. And the property of this polynomial is that if I take an element in the set and evaluate the polynomial in Y, we get 0. If I take an element, we take an element that does not belong to the set and we evaluate the polynomial in Y, we get a number different from 0. Now, if I have the encryption of the coefficient of the polynomial, so A0 and 1, A2 and AK, we can compute the encryption of the polynomial evaluated at any value Y. And I'll show you this in the next slide. We just use the property of the homomorphic encryption scheme. I omit the public key just to simplify the notation. So we have the set. S, encoded as a polynomial. So A0 plus A1 times X plus AK times X to the K. The encoding of X at this point is the encryption of the coefficient. So we have encryption of 0, encryption of 1, up to encryption of K. I want to compute the encryption of P evaluated at point Y using just the encryption of the coefficient and knowing, obviously, Y. How can I do this? Well, we just express the polynomial as the sum of this monomial. This is the encryption. I have this is an encrypted form. I've seen that the encryption of the sum is the product of the encryption of each single term. Then, if I concentrate, for instance, on this part, I have the encryption of a coefficient, AQ, that I don't know, and a constant, y2 squared is no. Since I know y, I know how to raise it to the square, and these values can be rewritten as the encryption of A2 raised to y squared. So knowing the encryption of the coefficient, I can compute the encryption of the polynomial evaluated in each point, in any point y I want, just computing what is written at the bottom of the slide. Each encryption is no, y is no, and I can raise y to the power from 1 to the k. So the protocol goes as follows. We use Alice public key PK. All the encryption are considered under Alice public key. I can Alice compute this polynomial, send the encryption to Bob. Bob can compute these values from each W belonging to his set. He can evaluate the polynomial P in W, multiply times a random value R, and add his value W. We can do this in a simpler way, as the sum is the product and the product is the power. So the encryption W can be computed. The encryption of the polynomial evaluated in W can be computed as we've seen in previous slides, and then we can just raise to the R this value. Send back this evaluation to Alice in a permitted way. At this point, Alice can compute the intersection just simply by computing the intersection of the set SA and the decryption of the set received by Bob. Let's see why. We have to recall that the polynomial evaluated in Y is 0 if Y belongs to the set, and different from 0 if Y does not belong to the set. So the encryption sent by Bob are equal to encryption of W if W belongs to the intersection, since this part goes to 0, and so there is only the W is left. Or if W does not belong to the intersection, the polynomial evaluated in W will be a random value, times a random value is a random value, plus W is still a random value. So Alice will get garbage. Decrypting this value, it will get either elements in the intersection, or value completely random. But why we use polynomial? It seems that this protocol is much more complicated. Well, because we can compute the more complex function. It's simple to add payloads to the elements in the intersection. For instance, in the protocol, we compute the encryption of R times the PW plus W. We could concatenate this information to the payload, and payload could represent some information associated to X. So when Alice will decode this encryption, we'll get either a random value concatenated to a payload or a value in the intersection concatenated to the payload. Then she can use the payload as she likes. There are several private set intersection variants. The simple variant is private equality test, where the two sets have the same cardinality, and we can use Alice will get true if the two sets are the same. So if the value held by Alice and value held by Bob's are the same, or we can compute the cardinality of the intersection. So Alice will compute the number of elements in the intersection, not the elements intersection itself, or PSI-CA threshold. Again, this is a Boolean function. Alice will compute true if the elements in common are more than a threshold T, or there is this more elaborate private set intersection. And we can assume, just let me make a simple example. We can assume that Alice is a social network, could be Facebook or Twitter, showing advertisement, and Bob is a store. It could be Nike, Lotto, or Adidas, and we can assume that the same user registered with both sites using the same email. So, for instance, V and W represents identity of the users. They could be, as I said, email. And using this private set intersection sum protocol, Alice will compute the number of users in common with Bob and the total amount they spent on Bob of Bob's store. So this could be considered as a measure of the impact of the advertisement campaign on the site run by A. There could be also enhancement. The first one is to consider malicious PSI, so player can follow arbitrary path in the protocol. They can change the message, change it in the protocol itself, or we can have a protocol where the sites of Alice or Bob is kept hidden, or authorized PSI. For instance, we can add Alice or Bob can add items in their set only if they are authorized. For instance, they could be signed by a third party. And let me show you, just briefly show, since I think I'm running out of time, a couple of examples. You can implement paternity test in Silico. It's not very complicated to do this particular application. Privacy preserving. We don't want to exchange the DNA. The DNA can be seen as a very long string computed on the alphabet composed by the symbols A, T, C, and G. And then we have two tools. One is called enzymes, and the others are called markers. The enzymes just break down the whole string in fragments. And the marker are a way to choose among all the set of the substrings computed using the enzymes, just a small subset, a subset of sites P. So we have some way of encoding the DNA strings in a different way, and the way is shown at the bottom of the slide. We can encode this part of the DNA using the marker and the sites of the marker of the fragment selected by the marker. So we can have this simple set composed by a number, which is the size of the fragment, and an ID, which is the ID of the marker. Alice can do this, Bob can do the same, and there is a threshold tau that states that Alice and Bob are relative, whether the number of the fragment selected by using the same marker are more than a given threshold, and the fragment must be also of the same size. So just modeling what is happening in lab in Silico, and using a private set intersection cardinality protocol, we can compute paternity test in Silico. Another possibility is develop a plagiarism detection system in a privacy-preserving way. In this case, we use the Jacquard similarity, and we can say that the two sets are similar if the formula just shown at the top of the slide is greater than a given traction. If you look, we encode the text in sets. I'll show in a moment how we can do this. We can compute just the intersection of the two sets, and computing the intersection of the sides of the intersection of the two sets is possible to determine whether the two sets are similar or not. How we can encode a text to a sets? Well, we can use the trigram. Trigram means we can take the text and takes 3 characters each time. So we can use T each A, and then we can use each A Q, and so on. And for this is just an example from the quick brown fox jumps over the lazy dogs. We computed the set representing this sentence in blue. So once I have the encoding of the test, I can compute the Jacquard similarity using as a sub-protocol the private set intersection protocol. So we can detect plagiarism detection using private set intersection protocol, so without exchanging the text I want to check. There are several other application. On the left side of the slide, we see the application that we can run in a digital world, personalized advertisement, by biometric authentication. We can find matching in social network, or we can run other kind of genetic test. We can do all these protocol without privacy in a privacy-enhanced way by suitably using private set intersection protocol or some of their variant. Let me conclude with the search that I have done this morning. I just searched on Google Scholar the term private set intersection, and Google returned about 3,000 papers on the subject. And if we restrict the search to this year, the results are about 500. So this could be an indicator that is a private set intersection problem. The research on private set intersection problem is a hot topic in cryptography. And that's it.